Right. Hello, YouTube. Boy, it always amazes me when it actually starts up. How are you, Ben? How are things on that coast that you
I am
guys call the West
on
Coast?
the west coast, the left coast.
The coast where the sun sets instead of rises. Yeah.
Right. Um, yeah, things are good. I, I, I'm trying
Back
to
in your
maintain,
office? New office?
yeah, trying to maintain a positive, upbeat attitude. I still don't have proper internet connection here. I am. I ended up paying $20 to get on the Cox Wi-Fi that they've set up in this side of the building until AT&T come and run their cable from the street. They have to run another fiber into this half of the building just because I asked to have AT&T installed, and it wasn't
Oh,
there yet.
cool.
They had it on the other half of the building, just not this half where I am. So I have to wait.
So
It sucks.
we have to
But
warn people that you could cut out then while we're talking,
yeah,
and I'll try and keep us going. And if you disappear for too long, we'll just call it a day.
yeah. But if I drop out, I'll do my best to just jump right back in.
All right.
Um, so yeah, how are you this week? We're looking at a
Good.
book.
Good. There's a yeah. When did this book come out? I was going to say here's a new book, but I don't know if how new it is. But
This is
Eric
quite,
Bogatin's got a new book out.
yeah, he's quite the prolific signal integrity guru. Um, this book was published in 2020 by Artec House.
All right, and you have one.
I have one. I was at PCB West, and during a lunch and learn sponsored by Polar, because I guess Polar helped sponsor this book, because Eric refers to Polar Instruments software in the book, for layer stack design and PCBs.
Right.
Um, it's not the only thing. It's not just a marketing for Polar. It is actually a good scientific textbook. But they were giving some of these away, and I answered a question or asked a question during their presentation, so they gave me a book,
Oh,
which is
yeah,
great
that's
because
cool.
it's an $80 book, as you see there. But this is
Yeah,
a really good book. Let's look at it closer.
that's a sexy cover, as you and I were talking before the
Yeah,
show.
hot pink on a deep violet background. What's not to love
And
about that?
and the title leaves no ambiguity as to some of the things we'll talk about in the book.
Yep. Bogatin's Practical Guide to Transmission Line Design and Characterization for SI Applications. There is one thing I really do love about this book is that all throughout, I haven't obviously gone through the whole thing. I've just thumbed through it, and I will keep it as a good reference, and we could maybe refer to it here and there on the show too. There's a couple of things about this I really appreciate that Artec House did. One is full color printing. Every page, it's not glossy, expensive paper. It's just like regular laser printer paper, but
Right.
every page is full color. So you don't
Right. Right.
lose fidelity or information around the images and the oscilloscope trace and TDR trace captures. And he covers the whole gamut of how to use TDRs for transmission line designs targeting printed circuit boards. So if you want to learn time domain reflectometry, this is probably the best book on the market right now. And there's a lot of photos of his test boards and deep explanations. And every simulation he runs is done in Cooks, QUCS, which we've talked about a little bit before. The Cooks is an open source, so obviously free, simulation tool for RF microwave signal integrity, mixed signal, analog digital. It's nowhere near as easy to drive because typical open source software,
Right. Right.
it's got some quirks because it doesn't have official product management like commercial software does. But of all the open source circuit simulators out there, Cooks is, I reckon, probably the best you can get in the free software domain. And every chapter he's got like problems and solutions using simulation that you can do in Cooks. So it's a pretty
Right.
good book.
Right. What
Eric
didn't you
ask
mention?
me to
There's
promote it, by the way. It was new, and so Bill and I were talking about it.
yeah.
It would be really nice if people like that wanted to sponsor our show. That would be cool. But we'd just probably be happy with people subscribing and coming back to watch each week and telling all the other engineers and electronics enthusiasts about it, so that we can grow our viewership, because we like doing this.
Yeah, it gives us something to do on a Friday, and it's keeping my brain cells alive as the ravages of time kind of degrade my brain here.
The people that come and then join the Discord, the ongoing feedback is this is actually, we talk about interesting and helpful stuff, and people learn a lot. So
right,
if people are learning,
there is
that's the reason to do it. So yeah.
Right. So matter of fact, you mentioned Discord. Let me I will put the Discord link into the chat channel here while we're talking. So now tell me, before I do that, so you mentioned Cook's in here. Does he talk about other open source software? You're going to talk about that a little bit here today yourself.
So far in the chapters I have looked into, he only mentions the commercial stack-up design Polar Instruments software and Cook's, which is free. And then other than that, I think just the tools that you can download for free from the Teledyne website, because Eric is kind of like a Teledyne LaCroix ambassador.
Right.
And so, he's a professor at UC Boulder or something like that, and he teaches this stuff. That's his main gig. But he does have some kind of relationship he's had for a long time with Teledyne. I think he used to work for them, and maybe when he went to be the professor or work at the university, I think they maintained that kind of relationship. So when I see him presenting at DesignCon and shows like that, he's usually doing it with a Teledyne t-shirt on. Because he's like a subject
and a ball cap.
Expert, not just for SI, but also how to use their tools.
Right.
Their TDRs.
So before I forget, I just got off the phone with a very special friend of mine, Terry Ryan, who did BASIC and several of the old Commodore machines. Terry, I just posted the Discord in the chat channel. If you see it, join us on our Discord. People would love to hear from you, or you could just lurk. I know you're a big lurker. But Terry, I don't know if you've seen things like this, but this is some of what we've been talking about. A guy named Johan Grip redid the whole C128 PC board, and he actually decapped all the chips, and he's looking at our old MMUs and PLAs and stuff, trying to figure out just what the heck we were up to 35 years ago. So definitely check us out there in the Discord channel. So
yeah, and Terry, what a genius. It would be great to have you on as a guest if you could ever spare the time. But we know people lead busy lives, but we know that our audience in particular are mostly, or pretty much all of us are massive Commodore fans. So come on.
Or at least we've heard the name, It's been so many years.
My first exposure to a Commodore 64 was at my cousin's house, actually. And I forget exactly how old I was, probably 10. And they just brought it home from Kmart. Remember Kmart?
Yes, I do. Blue light specials. Yep.
So Kmart was still a big deal, much bigger a deal in Australia. Walmart didn't exist there, but Kmart did. And Kmart was selling Commodore 64s like hotcakes. And
bubble wrap, we called it. Yeah, the bubble wrap channel.
And so I remember that, spending the whole afternoon typing in the example BASIC game that was in the user manual.
Right.
At the end of the user manual, it was like you could make your own game using BASIC.
Right.
And it was all character graphics, and it was a balloon that you had to float up between the clouds. And if you touched the cloud, it was game over, because the cloud would pop the balloon if you touched it. So was just a character-based graphics, and we spent the whole afternoon typing in the basic code from the book.
Did it work?
And it worked. Couldn't believe it. Like we typed we typed it in accurately.
Back then, you people did type in lots of programs. They'd see them in Run magazine and whatnot, and you type in a whole thing only to find out that there was a typo or multiple typos in or you'd have to wait 2 months to get the whole program. You know, it'd be half in 1 month and half in the other.
Oh, I know. So frustrating.
Right. Or you'd load it on a cassette deck and you'd wait and the cassette would not ever load.
I thank the Lord for compilers and debuggers and all of that we didn't have in basic home computers back in the day. But
we actually,
anyway.
One of the guys wrote, a guy named Hedley Davis wrote a yet another compiler. We could compile the C128 code on a C128. And that to me was really cool, that this home toy machine could run a 6502 assembler and assemble its own EEPROM, and you could then do a difference between that EEPROM and its own ROM, and it'd go, yeah, I'm the same. And so it was 100%.
Powerful. That is seriously powerful. Yeah, to run a compiler on the target device, and it wasn't long. Like it was computers like the C64 and other CPM machines of the day running Z80s that probably the first native compilers were built on, other than for mainframe systems.
Right.
Yeah.
And you mentioned the Z80, of course, the C128, you didn't have to decide between which one, you had both.
Yeah. Yep.
Yeah, and Terry was our CPM user when I first got there. 8-inch floppies, hard sector. Do you remember what hard sectors are on floppy disks?
No, refresh my memory.
So there used to be a soft sector is where there's one index hole punched into the disk, and there's an opto receiver, and it'll index off of that.
Okay.
Hard sector is where there's a hole punched for every sector. So you actually see a whole row of holes going around the opening in the thing.
Yeah.
And the Xerox, which was the CPM machine we had before the 128, in our lab we had a Xerox machine, and Terry Ryan was the guy that used it, that I remember. They took out the format command. So the only way you could buy discs was Xerox formatted discs. You couldn't buy a blank disc, put it in, and format it. So
That's
somebody disabled
crazy.
the software to sell hardware, to sell media.
That sucks.
Yeah, it did suck, kind of.
That kind of thing. But companies still do that all the time.
Still do that kind of
ways. Hey,
right, like right to repair and stuff. Yeah.
Yeah. It's exactly. It's a little bit better than that. That was bad back in the day. It's better than it used to be, but we still, like, for example, putting people on a subscription plan versus having perpetual licensing.
Yeah.
But at the same time, it forces the software company to keep adding value, because if you don't, people will just leave at a moment's notice. With no explanation, no feedback, they'll just be gone. So if you it's good for both. In certain situations, it's good for both the consumer and the vendor to have that. But I feel like in some industries, like telecommunications, we're just getting gouged all the time, and it's unfair.
Right.
But whatever.
Right. So one of Terry's rules was he would not use Commodore brand floppies, just because they were so unreliable compared to our needs, right? I'm not saying they were trash, but they weren't as good as other people's 5 1/4 floppies.
They weren't Memorex.
Right. Well, for example, we used Memorex. So Terry had to explain to purchasing why he needed brand X, verbatim floppies. And then they go, well, here's your Commodore floppies. He'd have to say, no, I ordered verbatim. And they turn around, oh, of course you are. Oh, here's your Commodore brand floppies. And so we'd end up having to buy them ourselves sometimes, but we just didn't trust the Commodore media. for what we were doing. I mean, it might be okay to copy a game, but you didn't want to, you didn't want to lose the C128 compilation or the TED source code. And at one time, that was all on floppies. We just didn't have hard drives like they do today, back in 82. We didn't, at least.
Yeah.
So, and that was back when a Winchester 10 meg drive was horribly expensive.
Oh, they were crazy. It wasn't long though before the little, and this is, if anyone ever reads, this is another book I highly recommend for anyone who ever wants to be involved with technology business, the business of technology. So you're an engineer or a technologist and you're an enthusiast and you know how everything works or learning it, but you want to get into the business of it. A book you must read is The Innovator's Dilemma. The Innovator's Dilemma is about this thing that's been discovered where new disruptive technologies will displace established technologies. So the home computer became the PC, the personal computer. The PC destroyed, almost completely destroyed the mainframe market. Now, IBM and one or two other specialist companies, big companies like IBM, they still make mainframes.
DEC. Yeah.
Oddly enough, they do it, but that's kept alive only by, for example, the finance sector, where they need ridiculous computing power to have unfair advantages over their competitors and normal people like you and me on stock markets and so on. Right. They need crazy computing power to support all the financial transactions of the world. So, and their current mainframes aren't like old mainframes. It's not a big computer with a CPU card that's a CPU made of high-speed discrete ECL logic. It's a CPU card will have multiple dedicated silicon cores on it that are all massively parallel. So they have a mainframe that's really just more like Amazon's compute clusters in the cloud, really. It's kind of a similar deal. But anyway, not to go off on a tangent there.
No, I like tangents.
You reminded me of The Innovator's Dilemma because of your comments about floppy disks and then hard disks, and Winchester disks were expensive and unreliable and small, and the hard disk
crashed.
The hard disk manufacturing problem is the first chapter of the Innovator's Dilemma book, because it's talking about how Seagate and Western Digital basically turned the hard disk industry on its head by making these little 3.5 or 5.25 inch hard disk drives for personal computers that eventually got fast enough and big enough in capacity that it wasn't worth spending 100 times or 1,000 times the cost for a traditional hard disk drive that was used by a mainframe computer like a VAX, where they
like a multi-platter thing or something.
I remember my friend Andy. I used to work at Digital Equipment Corporation just after they were acquired by Compaq, and my friend who was my boss, Andy Hobbs. Andy, I hope you see this one day and enjoy the show. He had this. He started out his career 15 years or even 20 years earlier at Digital Equipment as a technician renovating hard disk drives for the mainframes. And he would pull apart these whole massive assemblies and actually literally use alcohol and clean the platters, because back then you could actually do that. And
touch the platter,
actually touch the platter and clean it because they were big and low capacity, but they were really fast. They had this hard disk product that had a really large diameter disk, and only the outside edge of it had magnetic material, and they had a fixed head, and the head didn't go in and out. It had one what's the word? It's not sector, right? It's
right. What is that? It's not the ring. It's the ring.
Track.
It's the track.
It had only one track on both sides, and then they had several of those disks with multiple heads. And it was used as an intermediate high-speed storage. So it was a hard disk it had lower capacity, but the value of it, like this thing was going at tremendous speed, and it was used as kind of like a magnetic cache that had some properties where, like, if the building lost power, the data was still on the disk from the last operation. So
as the disk spins to a halt. So,
and
well,
specialized products that were all turned on their head by cheap memory and cheap, low cost, cheap desktop hard disk drives.
Right.
So
now, you were talking about old computers. Do you remember Cray? You're talking about old computing power. And the pinnacle back in the day for us was Cray. And, of course, they had different math. They could do vector math operations, which was, hardware dedicated to a certain kind of math. But I actually did a consulting gig for Cray research, which to me was like religious. They caught me. There's a picture out there on the internet of me licking a Cray. A more modern day one. It's like from 6 or 7 years ago, but I'm like, Crays were it, and nowadays your PC blows a Cray away.
Well, Crays were it. Crays were made famous by the movies because they were the first computers used for 3D motion graphics. And,
Tron and those things.
Tron was done using a Cray, and the last Starfighter had special effects done using a Cray.
Yeah.
And The Last Starfighter was an awesome movie. When I was a kid, we loved that movie. So if
First
anyone
time I
hasn't
saw
seen it, super cheesy, but watch The Last Starfighter. There's a spaceship in it that kind of has this form that even looks like they refer to the ship as she or her.
Right.
And I guess a lot of captains of vessels do that, actually, come to think of it. But whatever. Anyway.
So, I was going to say, I saw The Last Starfighter. I was actually coming back from the Tokyo office when I worked for Commodore, and it's like a grueling 18-hour flight, between 18 and 23 hours, depending on whether you went a polar route. And suddenly there's this beginning of The Last Starfighter, and I was the happiest engineer on the plane for 3 hours because I got to watch, computer-based graphics and realize what I was watching. So, but I was going to say, the work I did for Cray was we had a CDC multi-platter drive. Seymour Cray came from CDC, which in addition to doing the computers, did the multi-platter disks that you're talking about. And the way they would test one of the drives was they had to use the Cray itself to walk patterns through the disk drive. And that's a horrible use for a Cray computer that gets billed out per second, right? And so what we did was I took a TI TMS 340 or 320, one of the two, and I made an SMD bus analyzer where you unplug the drive from the Cray and plug it into this box. I don't want to say it was a row of toggle switches, but it was almost a row of toggle switches where you'd walk patterns through and debug whether the media was any good or not. I mean, it's very crude by today's standards. But yet, here we did a contract job for Cray when I was like 27, I think I was at the I had just left Commodore and was working for a contract house. So what do you have in your picture here that's on your screen?
No, you just got me to thinking about my first PC that I owned. So the first PC that I had access to, that was my dad's 286 made by Philips. And we've talked about that in a past show. But you reminded me, my first own PC that I actually owned, I got at some kind of auction clearinghouse that was taking, I had a summer job and they were taking old computers that were ex-government. So they went to auctions and bought up tons of computers, pallets of them, that were being clear out of the police department or the city of Sydney or wherever. And so they had some genuine IBM PS2s and they had some Memorex Telex PS2 clones. And if you recall, the PS2 could run Microsoft DOS and MS Windows 3.1. And I had this summer job where I had to try to get these things working. Most of them hardly even booted, or had lost their configuration utilities. And if for those that don't know, the IBM PS2 and its clones were an advanced technology that went beyond the PC-AT. When IBM released the 386, other companies like Compaq and Digital and Taiwanese companies who were encroaching on the PC market, because the PC had an open architecture called ISA-bus, it meant anyone could start making motherboards and selling computers and not pay IBM any royalties. And IBM's bean counters got annoyed with that. So they went to the engineers and said, make the next generation so people can't copy it.
Right.
Or if they do, they have to pay us a royalty. So they went and invented a whole new architecture called microchannel. And microchannel was the first official plug-and-play architecture where you didn't use jumpers to set addresses or anything like that. And it was higher speed, and it had a better bus configuration where there was regular grounds and VCCs along the bus slots, so that you had better signal integrity. And so buses went from being 1 or 4 megahertz to being 8 or 16 megahertz, and they went from being 8-bit to being 16 or 32. But the problem was everything had to be configured by software. And if you didn't have, and you had to have not only the driver disks, but you had to have the BIOS configuration utility for the motherboard and for the add-in cards that you had. So I managed to snag a 386. I noticed as I was putting these machines together and getting them working so this place could sell them off as cheap computers to home buyers, and a lot of people were buying them. There were a few that happened to have come from some kind of engineering department, and I found a 386 microchannel computer by Memorex Telex that had a 387 coprocessor. It had an additional memory card that was a microchannel card that was covered in SIP modules, much like the one you see here. This here was some sort of add-on card for I/O. This one looks like it's probably analog or audio or something like that. I had this extra card like this that had memory chips all over it. I'm like, I'm going to get this one. I'm keeping this one for myself.
And there were two kinds of memory, right? Extended and expanded?
Yeah. Well, that was in DOS too, but microchannel also made it so that you could have more extended memory, or whichever one was the faster one, because the bus was wider.
The flatter one, yeah.
It's a 32-bit bus, and it was higher speed. And so, so I reserved that machine, and I asked, how much do you want for this one? I want this one for myself. And it had a decent XGA video card in it and all this cool stuff. And they said, $300 for that one. So I paid them my week's earnings for working there for that week to take that one computer home. And that was my computer for the rest of all my college years. And I got through on a 386 running IBM PC DOS and Windows 3.1 and doing 8051 development on it, playing the odd game here or there, and fighting tooth and nail to get the cards to work in it. And I had the configuration utility, but it had this additional I/O card that had like a 37-pin D connector on it, which I didn't know what it was. It was made by Everex.
Right.
And there was that other memory card that had all that extra memory, and for no matter how hard I tried or what information I sought on the internet while I was at the college library, I could find no downloads that would help me get that memory card working. It was so frustrating because it had all that memory just sitting there, and it had lost its the button cell battery that kept the CMOS programmed to keep the PC's configuration. Ran out, and it lost its configuration, and I could never get it back again because I didn't have the configuration utilities. So eventually I pulled all the chips that were socketed off the motherboard and put it out to recycling. And this happened maybe a year and a half, 2 years later, and then by then I was putting together a 5x86 machines. It didn't matter, but
Yeah,
Anyway, those were very frustrating. Those computers were advanced for the time. Any PS2 or a clone, they were overpriced, and it was really
heavy.
hard.
They
You had
they
a
were
problem, you
yeah,
couldn't you couldn't get any help. There was no internet back then to speak of. There was, but there wasn't
right.
nearly
And
anything online.
they were
Just
real
fine.
heavy cast housings. They were made to be assembled by robots,
Yeah.
which was novel at the time. But if you banged your ankle carrying like a PS2 Model
Oh man,
80,
it was a boat
you'd
anchor.
hurt yourself. Yeah.
It's a boat anchor.
Yeah. Now, didn't what was the other operating system under DOS? Was it OS2 or OS9? I can't remember.
OS2.
It was OS2. What was
OS2 was,
OS9?
I don't
Where
know
did I
what
get
OS9
9 from?
was.
Yeah.
It was
Okay.
OS2. So OS2 was IBM's own operating system,
Right.
right? That was specifically for the PS2, and it was a true GUI. Unlike like Microsoft Windows 3, excuse me, was a GUI, but it ran over the top of DOS. So you'd boot
Right.
to DOS, and then you'd launch Windows, and it then you'd get the Windows 32 extensions that would later run 32-bit programs, Win32s.
Right. Right.
Once 32-bit, 386s came along, and then, but OS2 was true 32-bit, or I think the first
1632.
version,
Yeah.
16 and 32-bit, boot straight into a GUI, and ran on a PS2, but
Yeah, there was a CLI with it too. I remember a guy had at the local Wawa, which is our local convenience store, and this is 20 years ago, had a ATM open, and I look in there, and in there it was the computer was at an OS2 prompt, and I had to laugh. It's like, oh, you're the people that use the OS2. So you blurped there, but you're still moving, so you're still on the internet with us.
yeah, it disconnected and reconnected automatically. So.
Really, really fast. Hey, so before we jump into the, you finish up what we started last week with your presentation from PCB West, I wanted to show you something. You've been talking about World War II airplanes, and you've talked about railroad cars, scale modeling and stuff. So I'm an airbrush kind of guy, and I had done this. This is an F4F Wildcat, a Tamiya, probably Tamiya. But this was something I had done to make it look weathered and to make it try and look
so
realistic.
Good. That looks amazing, Bill. You got skill with the airbrush. Just saying.
Yeah, you spend an equal amount of time cleaning the brush as you do using the brush. It's the only downside. And if I could talk my son into cleaning the brush for me, like $5 a pop, I would sit there and have 2 airbrushes and have him cleaning one for me.
Does he do any of this kind of modeling stuff?
I'm trying to get him into it. He's very good with his hands. It makes him a good surface mount solderer. So if you set something in front of him in the instructions, he'll put it together better than I can these days. He's very dexterous, and he's got his eyesight still works to his hands. That eye-hand coordination that's broken in me being an old timer now.
My son's an artist as well. I think he would get right into that. He's talked about doing weathering, but he wants to do it with other bizarre things like his rip surf. He wants to make his rip surf look weathered. It's like, dude, just ride it. It'll get weathered.
Yeah. Actually, if you watch, Adam Savage from Mythbusters has a channel out, and sometimes he'll do something. He used to do virtual realistic effects. I forget what they call it. Not graphics effects, but where they make the actual... Yeah, the actual models that are usable on stage or on the shot, and they weather those. And he talks about how he makes the weathering tell a story. You know, how he'll burnish something and how he'll use a filter to reduce the contrast of stuff. And so part of that plane I showed you, there's filters on there too, so that it looks a little faded. And some of the models I do armor models. You really go for it. You almost don't want to see the camouflage under it because it's so mud covered. It kind of just fades in a blotchy thing. And
or
so
you
maybe
probably get a fine tip soldering iron and gouge little
They do.
little
They do. They'll
things in
take
the
a
side to make
combination
it
of.
look like it's been taking, armor-piercing hits.
There are videos on how to do that, how to make it look like it splashed when it hit, and they'll do a combination of Dremel tools and a soldering iron, and the whole thing is scale, right? You don't want the bullet hole to be, or the hole of whatever that armor-piercing shell was. It needs to still be in the scale of 1/35 or 1/48 or whatever your model is. So there's actual things on how to do, damage like that. And I saw one real cool one, and then we'll get onto your thing, where they showed a burnout tank, and they had the colors just perfect. When something burns, it actually turns a white scaly color, and then a gray color, and then as you get to the edges, you start to see the unburnt colors. And I looked at this plastic model, and I'm like, it looks like he took a torch to it, which of course he didn't, but it was really fantastic. So very cool stuff out there. So, all right, so let's jump in. Last week, you had started showing us some of your PCB West demonstration you did, and it was about. Tell us what the class was about.
Well, it was just an intro to PCB antennas, and it wasn't long enough. I need to make it a full day class, or a half day class, and have some more time to actually walk through some design exercises. But that's basically what it was. 2 hours of, these are the antenna basics. We talked about some of that last week, and then how are these actually implemented, and what are the things we care about measuring, and so on. So I was, using the VNA and showing how you want to tune different types of antennas. But what I have here is, so we're looking at some of this, and this is some simulation results. And this 3D field plot here, which is the same as the one in my slide title, actually.
Right.
This was actually done using free software called OpenEMS, which some of you may have heard of. OpenEMS is an open source finite difference time domain field solver. And so what does that mean? It uses the FDTD technique, which was invented by a brilliant postgraduate engineer called Yi back in I think the technique was first published in the late 60s or early 70s, somewhere like that, when it had to be done on mainframes. But now, you can just do it anywhere, and it's probably the most common numerical modeling technique for electromagnetics. There it is. And you've got a picture there of the Yi cell. The Yi cell is kind of the crux of it. It's what makes it an efficient and easy, computationally easy thing, is that you divide the entire three-dimensional, or you could do it in 2 dimensions, model into these voxels. A voxel is a 3-dimensional pixel. A voxel is a cube. Right. And in the center of each surface in the Yi cell is, say, the 3 planes of the voxel for your H field, and offset from those in the three of the corners of the voxel are your E field locations, and that works just naturally because E field and H field are always perpendicular to each other. So I'm not doing it justice, and that's a very hand-wavy way of putting it, but there's other videos on YouTube that describe FDTD really well. But OpenEMS is an FDTD solver written by one or a group, but I think it's really just one guy, Thorsten Liebig. I hope I said that right. He's German, from a university, one of the universities in Germany. And it runs under MATLAB as a plugin, or GNU Octave if you don't have a MATLAB license and you want to use GNU Octave. It is multi-threaded, so it will simulate pretty quickly. FDTD notoriously slow as an algorithm. When you don't divide up your thing into voxels properly, you end up with too much, and it takes forever to simulate. You get a very accurate simulation, but it takes a long time.
Okay.
So the techniques in optimization in commercial software focus on how do we just simulate the bits we need and get an accurate enough result so that it doesn't take forever. And that's why, and then they wrap a really nice graphical user interface that's very easy to use and modeling environment around it. So that's why tools like HFSS from ANSYS, or what's the other one? ADS, Keysight ADS, and there's a few of them. They're all very, very expensive. The underlying algorithm is not what you're paying for, because those are well-known, well-published. Anyone can pretty much, for the most part, use those numerical techniques and write your own code. The secret sauce in the commercial tools is the optimizations and ways of accelerating it, namely, and the nice user interface around it that makes it easy to drive.
Right.
But I was going to show real quick. This is my GNU Octave, and I have OpenEMS installed, and this antenna pattern here is for an inverted F antenna.
Whoops! So, I just deleted the wrong thing. Keep talking, but I have to get you back up on the screen here.
Yeah, it's okay. Let's go to where's my recent. and one of our Discord members, Nix, just got some RF synthesis tool, a commercial RF synthesis tool, and next week or the week after, whenever it works, I was going to. He offered to synthesize some filters for me using the tools, the software he just got, and so I'm going to come up with some specs, and he'll synthesize a design and simulate it, and I'll mill it on the mill for like a hair.
Right.
We'll do a hairpin filter or something, and we'll compare. I'll put it on the VNA, and we'll compare it to the simulation and the synthesized version.
I'd love to see the mill too. If you can ever put a camera on it, or actually just shoot a video even.
It's just on the other side of that acoustic wall I just put up. So it's there. And once I'm set up on the lab half of my office, I'll be able to live stream from that side.
Okay.
And I'll have different cameras and things. Like, I'm aiming to get to where you are with your basement, but it's
right. I got cameras everywhere here. Yeah.
So anyway, let's have a look. This is the IFA. Oh, this is the results. So I'll go up one. So with this tool, we start with code. It's MATLAB code, and so if you don't like coding, well, sorry. Cooks. There's a version, a derived work of Cooks called Cook Studio, and they put the OpenEMS into Cook Studio. So that project's exciting to me, because what they're doing is they're heading towards putting the GUI of Cooks around OpenEMS, so we can do FTTD. It still needs a lot more work. It needs more GUI stuff done to where you can design the 3D structure. But what we have here is we're defining the 3D mesh. We're setting up what type of simulation we're using, boundary conditions for. There's different types of boundary conditions. So we set up a cube, which is our space in which, that's the domain in which we're simulating, and we have the materials configured within that and their boundary conditions. So the edges of the cube might be a perfect electric conductor, or what's it called? A perfect absorbing boundary. I'm not using the right terminology for that right now.
Kind of like anechoic.
It's
however you
basically
say it.
like a virtual anechoic chamber that absorbs everything perfectly, like reflectionless. You have a boundary around it that like it just attenuates so nothing comes back out of it. And then we set up our simulation box, like, and the edges of the box is where we effectively measure things like antenna, field strength and all that. Then we're adding things like adding the perfect electric conductors or metal of the actual conductors, and we're adding other box shapes, which are our things like feed element, the radiating element, and so on. And we add our insulators, and it comes with this additional executable he created that's like a 3D visualization tool that lets you view what you've defined in code to make sure it's correct before you actually execute. And then we define input ports and output ports or measurement ports and their impedances, and we run the simulation and we gather the results in this one XML file, and then from there we can plot the results, like plot impedance versus frequency. We can plot S11. I keep saying S11 and getting corrected by people there, but whatever. So that's kind of what it looks like, and I can execute that by hitting this from the text editor in Octave, and you can see it runs this additional executable. It's our 3D visualizer. So I have a bit of printed circuit board, and I have plane layer, and then I have copper for the antenna radiating element, which is this part here, it's a half slot. This is the feed line, and the feed points here with the feed port at 50 ohms driving a sine wave. And this is the matching inductance that, with a F antenna like this, which is half a slot, you adjust the feed point up and down to get a match, an impedance match. And you adjust the length of the radiating element to get a frequency tuning. So the longer the radiating element is, the lower the frequency, because you're increasing that. This length here is a quarter wavelength. And then we adjust this inductance to ground on this side of the feed line to get our 50 ohm match. So that's done. I exit out of that, and it keeps executing. If I look at the command window, this says, okay, so now it's actually launching the FDTD, and it starts to converge on a solution. And in my outputs folder here, it's generating H5s are a sort of industry standard electromagnetic field output format. It's like a text format that just has the numbers in it. And this is running multiple threads. I don't know if it says how many threads. Let's see. It doesn't say.
Yeah, I don't see.
It says it's using SSE and multi-threading. This one doesn't take too long. If I open up my task manager, let's have a look. Here's task manager. You see it's, I sort by CPU, see Octave is the parent process, and it's running OpenEMS as a child. Let's see. It could be using more compute. Oh, I think it's already finished. It's already just finished. So it's actually already done that, and now this is our S11. So the tuned frequency of the simulation is 2.4 gigahertz, and this is my impedance, real and imaginary impedance. And you see the resonant peak at the tuned frequency, or a bit below actually. And this is the field plot, which Why can't I swizzle that around? There. It's kind of a counterintuitive field plot for an inverted F antenna. You would think that its radiation is strongest out from the edge of the board that we looked at, but actually it's strongest in the opposite two corners, and then away from the radiating element. And of course, the corner where the inductance back to ground is, there's almost no radiation. And so this is just one of the bottled examples that comes with OpenEMS. I didn't develop the code for this particular one, but it gets you started. You can see how to generate your three-dimensional shapes of the antennas on the board. And I think it would be good to have a project to basically parameterize a bunch of really common antenna types and just plug in the numbers. Like, oh, I want a meandering inverted F antenna that's tuned to 2.45 gigahertz. And I specify that frequency with a 50 ohm feed line, and then it calculates from that the dimensions as a starting point and then runs the simulation.
Right, right.
So I'll close all of those. That's finished. So you see it didn't take too long, but it dumped all these outputs into this folder, including a VTK. So one of the things that OpenEMS does is it gives you an output for this visualization toolkit, which is it's also an open source kind of standard scientific visualization tool set. I thought I'd opened ParaView. ParaView is a program that uses VTK. Let me, and it's hard to use. I'm still learning. Yeah, let me run that. This is ParaView. ParaView is really powerful and very flexible, and so as a result, it's very confusing and hard to use. Because it's not just for viewing electromagnetic fields, it's for visualization of any kind of scientific data. But let's open that VTK. Let's see. What I want OpenEMS. Here it is, the VTK. And then by default, I don't know why it does this. You open something and it's not visible. So you have to click on the eyeball. And there's the default view of the 3D antenna response pattern in ParaView. So it's easy just to get that working. It took me ages to figure out, but what I actually wanted was a different color scheme, like rainbow.
Right, right. Oh, cool.
And then I wanted to superimpose that with the 3D design, and I found that to be very difficult.
Right.
But if I go back to this and if I run that again, oops, where's my editor? If I run this again and I just want to run the 3D plot tool, right?
Right, right.
I just selected the wrong thing there, but whatever. This is my 3D model. This tool also has an option to export to VTK, which can be opened in ParaView. So I export the VTK, I'll put it in the same folder. I think that's done, and I close that. This is I'm still running that, so I want to quit running this. Let's go back to here, and I can open Now I can open the, let's see, which one is it? EFA, VTP, and ground plane, and substrate. So open all of those. Now let's turn that off and turn these on. There's my F antenna, ground plane, and substrate. And they're all different colors, so I'm going to have to there's the I'll change the substrate color. Let's see. Make the substrate, I don't know, PCB-ish.
Yeah.
And then make it right. So ground plane, let's make that coppery and shiny. So that's our EFA, right? Now let's turn the 3D pattern back on and zoom out. The pattern scaling is kind of funky, but at least it gives you an idea of the direction.
You're right.
These are all set to the same XYZ coordinates. So counterintuitively, you get, and intuitively as well, you get no transmission directly out the back of the ground plane. Well, you'd expect that, or out the side of it. Counterintuitively, you'd expect, this is the radiating element, you'd expect lots of radiation out in this XY direction. But actually, that's where you get hardly anything. And the reason is that's a quarter wavelength open circuit stub, right? So the voltage at the tip is going up and down at a maximum peak, but the radiation from it's half of a slot antenna, and the radiation comes out most up and down in the Z plane all around. But that just gives you some idea of how to use, you know, VTK with open EMS to figure out, you know, this is the antenna radiation pattern, and it is scaled. It's actually scaled to gain.
Oh, okay.
So, but there's other, you can simulate it and get this data, and normally you just use the plotting features in MATLAB or Octave to plot it in a normal way. And there's also an RF toolbox from MATLAB and a clone of the RF toolbox for Octave that'll do Smith charts and all of that as well. And so you can take this data and produce antenna documentation that you actually have something real you can compare with once you put it on a VNA. So,
right. That's really cool, dude. It's a lot of work and it's a lot of writing, but that's really cool.
Yeah. And I'm planning on getting more into this as I write more and develop more of my class going into the future. And, you know, I don't want to talk too much about the future. I don't want to boast in the future yet when I don't know what's coming or what
right
things are coming my way, but I have some intentions to develop a lot more material around this because it's just lately become far more interesting to me, and I feel like there's a lot of people who want to know this stuff and don't know where to start. So,
well, could you write a book about this? Have you thought about doing that? What you just showed could be like that could be 2 chapters of a book.
It could, and probably will, but I don't want, like I said, I don't want to boast in the future.
Okay.
Didn't
want to take you there. Sorry.
Give me a year and a half, and we'll see where we go.
Right. So, well, we're actually out of time.
Writing a book is very difficult and a massive commitment.
Well, I got somebody to help me. That's the only way I was able to do it. Was I had a 50% author to take the, as I say, take the ravings of a madman and turn them into the scribblings of a madman. It's so. So we're actually out of time, and I do have to jump for a meeting here pretty quick. But this was excellent. We didn't get very far into your PCB West, which is good. That means next week we can finish your PCB West demo.
I think next week we'll do something slightly different.
Okay.
But we'll see.
Yep. We'll have to talk about that offline because I'm like a one-trick pony. We've all seen my trick, so we got to find something new.
There'll be more.
But I'm
hoping to have the rest of my office and lab configured, so we could probably do a bit of a tour, hopefully. Yeah.
Yeah. So very cool.
Yeah. Thanks for
Ben.
watching.
It was great seeing you today. Yeah.
Yep. Make sure you. I want to give away some stuff, and so I've got to. I keep saying this, and we have to actually do it. I want to come up.
I keep doing that too. Yeah.
I want to come up with some thing we can do where people who watch, I can send them some stuff.
You know what might be good for that is a PC board like that demonstrates a slot antenna or something like that. You know, something cheap like a PC board, and yet laid out talking about the principles we talk about here.
Yeah. Yeah.
And that'd be and even then just making the Gerbers available so people could get them themselves, you know, off our Discord or something.
Yep. But I'm also thinking, you know, some incentive to invite others to join us would be cool.
Right. Yeah, we definitely want to do that. So, all right, we will see everybody here next week. Goodbye, Ben, and great talking with you again.
Too, as always.